Good. Good morning. Um, just a couple of administrative notes before we get started. I posted some more assignments for you. I posted, let's see here. Assignment, well, if you haven't seen assignment 12 on two sample proportions, but I think you probably have because that's been up for a while. I posted assignment 13, which is the chi-square goodness of fit test, which we talked about last day. Now, we only had time to do one example, but there's another example in the slides. And so just an assignment to for practice. You will have to do a chi-squared goodness of fit on test 2, okay? And so so just make sure you practice that. But then I also posted another bonus assignment. Now you don't have to do these bonus assignments, but if you've missed a previous assignment or you want to improve your grade, uh, then if you do the bonus assignment, then of course your lowest grade gets replaced with that grade because your assignments are set to drop the lowest 2. So that means if you don't do these bonus assignments, this is the second bonus assignment that's available, and there will be, I think, one for sure, maybe 2 more, okay? And so, but one, I'm promising one more bonus assignment, and then we'll see how far we get. If you don't do it, no big deal. It's just for practice. Now, I did want to show you because there is a video here. Let's see here. So it does have a video to introduce the topic. It's an excellent video. He does a really good job. It's that Z statistics again, and and if you're struggling with any of the concepts that we're covering, then I'm sure he has a video for that. So that might be kind of a helpful resource. Okay. I also want to make a note about the labs. Okay. So here we are. Sorry, I don't have a pointer when I'm just in the browser, so kind of tricky to follow along, but Lab 9 is available this week, so that's the one that you're working on this week. Kind of tricky if you tried to do it yesterday, then we're just introducing it today, so that might have been difficult, but you have time to finish it, so that's fine. And then we don't have any labs for 2 weeks because of the holiday Monday and the holiday Friday, holiday Monday. It means that because we have Monday and Friday labs, that kind of makes a mess. And so then we have to cancel the labs for the entire week. And so then there's quite a bit of time for you to get caught up on the labs. But I'll make Lab 10 available over that period of time. So even though we don't have lab sessions, you'll still be able to work on it. And it introduces the final topic of the course, which I'm confident you'll enjoy because it's a really fun topic. Okay. And so so I'll post that and that'll be good. So I made a note. Now I have my pointer here. Where is it? There. So no labs for the next 2 weeks, right? So that's kind of weird. Just how the cookie crumbles. But Lab 10 will be available. And so you will be able to work on it just on your own time. Okay. There. Those were my administrative notes. We're starting chapter 7 today, which is inference for numerical data. Numerical data, we haven't dealt with numerical data since, let's say, chapter 2, right? And so where we introduced it, and so, but for numerical data, usually we're concerned about the mean, right? We want to analyze the average revenue, the average, all my examples are money examples, average sales, average whatever, right? So as soon as we want to talk about the average, okay, then That's the mean, right? It's been a while, but I do expect you to have those two linked already in your vocabulary. So this is section 7.1, and for the next couple of days, we're just going to introduce one section at a time. So 7.1, 7.2, 7.3, and they're going to follow the exact same format as the proportions, right? For categorical data, we said, well, what if I have one sample proportion? I want to compare it to a number, right? And then we said, well, what if I have two sample proportions and I want to compare them to each other, right? Or what if I have three or more proportions, right, that I want to compare? And so we'll do the same thing for means. We're going to start today with just having one mean that I want to compare to some number, right? And so the exact same format as before, just means instead of proportions. And so, and then we'll have two samples. Interestingly, there are two ways that we could have two samples, and so we'll talk about those. And then if we have time, which I kind of think we won't, then we talk about three or more means that we want to compare. So if we don't have time, then that's going to be a bonus assignment, just so you can see it if you want to. Okay. So one sample mean with the t-distribution is what this section is called. And so we're talking about, so the type that we're introducing here, I'll do this. The type that we're introducing today is one sample mean. Okay, so we've talked about one sample proportion, two sample proportions, three or more sample proportions, which is a chi-squared goodness of fit, and then so now we're doing the same thing. Now, I find that the hardest part when we kind of move from talking about proportions to means is, okay, well, how do I know what type of question it is? Because now what's going to happen is your first decision point is this going to be a proportion question or a means question? And so here, just consider these, and I'll zoom in. Proportion versus mean type of question. And I stole these from a different textbook, but I thought they did a good job of just highlighting the differences between the two. So members of a political party in Texas are considering giving their support to a particular candidate for election to the U.S. Senate. And party leaders want to estimate the proportion. Okay. And that will happen, right? So the word proportion will be in the question. And same thing, the word mean or average will be in the question. And so that's going to be a huge factor in determining what type of question you have. And so I'm going to highlight here what proportion of registered voters in the state that favor the candidate. I probably read that wrong. A sample of 400 registered voters in Texas is selected, and 160 of those voters indicate a preference for the candidate. Okay, and then usually we would just stop there because then you have all the information that you need. You have 160 successes and you have a sample size of 400, and then you can find your sample proportion. P hat is 0.4, right? 160 over 400. Whereas here, now we're moving into a means type of question. Okay. And so a tire manufacturer is considering production of a new tire designed to provide an increase in lifetime mileage over the firm's current line of tires. To estimate the mean, and I know what you're thinking, Emily, that's so ridiculous. I'm going to be able to pick that up no problem, right? If it's a mean or a proportion question. Well, it's not as easy as it looks, right? So that's going to take some practice. Okay, it will be in the question though. the mean useful life of the new tires. The manufacturer produced a sample of 120 tires for testing. So again, we have 120 as our sample size. Okay. And the test results provided a sample mean. Okay. Let's talk about that. I'll just do this. N is 120. Okay. And here, how do we denote the sample mean? The sample mean is denoted by X bar traditionally, or Y bar for some reason if you're in kind of higher level statistics, which we are not. And so doesn't matter. Anything with a bar over it is an average, a mean. And so X bar is 36,500 miles. This is our point estimate, right? And so we've used this terminology before, and all the same terminology applies. In fact, all the same things that we've learned for proportions still apply for means. Okay, and so that's what we're going to develop today. So these are kind of old slides that I used to use, and now I'm using them again, and they're a little bit more handholdy than I'm used to it now. But anyways, so we've talked about inference techniques. So inference, let's remind ourselves, inference techniques, which is a confidence interval and a hypothesis test for categorical data for proportions. And so today we're going to introduce inference for numerical data, for means. So when we analyze numerical data, we often want to analyze the mean. For us, it's going to be always. Okay, I'm just saying that because we, in theory, we could do other things, but for us, it's always going to be the mean. Okay, so X bar is our point estimate. And what are we trying to learn about? We're trying to learn about mu. So our point estimate is X bar, the sample mean. And the parameter is mu, the population mean. So I'm trying to learn about mu by using X bar. Okay. Now, I've got a blank slide for the formula sheet, and you know these slides are, well, here we are in chapter 7, but if you didn't see, the slides are all posted on Moodle, and they have been this whole time. Okay. So here I am on the formula sheet. I'll scroll to the very top because look at us go. We're picking through this thing. And so we finished one sample proportion and we did 2 sample proportions. That was a big day, right? But once we kind of got down to the nitty-gritty, this wasn't so bad. Then we did chi-square goodness of fit testing. And just a note, the chi-square test of independence is not tested. Not on the test. It's optional. I guess that's kind of hard to see, but it's optional. Okay. And then, but you do need the chi-squared table of critical values for both of these chi-squared calculations, right? Now, we're here. One sample mean. A one sample mean question. Copy. Gonna paste it in here. So, okay. Here, what this is saying is that the central limit theorem applies, and we can still have a normal distribution as long as we know what mu is and what sigma is, which is not really the case. And so this, again, I'll just make a note that this is really theoretical And you're not going to use this, not used explicitly, because we're using the concept. So I'm not going to say that we're not using it at all. We are using the concept, but you'll never use this in your formulas or anything. Okay, and so we're just using kind of the idea of this, the mean. Okay, so the sample means, what does it say? Follow a normal distribution. Hey, that's great, right? Centered on mu, so centered on the population mean with a standard error of sigma over root n. Okay, and so this is the spread of the means. Yeah. And so same kind of logic applies for the central limit theorem that we established for one sample proportions, but you don't need to worry about that. All we need is we need to be able to use the formulas and figure out what pieces go where. Okay, so we can make a confidence interval, surprise, surprise. Okay. Now, there are a couple of unknown pieces here, right? X bar, we know that's the sample mean, and that's still our point estimate. Okay? Uh, T star and -1, that's what we're going to tackle today. We're going to introduce this idea, but it behaves very similarly to Z star. Okay, it's just that it follows a T distribution instead of a Z. S, remember, is the sample standard deviation, and n is, of course, the sample size. Okay? And so here, whoops, x bar is the sample mean. T star, I'll just say, is the critical value, because we're going to talk about it later, but it is still the critical value. S is the sample standard deviation, and n is the sample size. Okay. And of course, S over root n is the standard error of, oops, of the point estimate, x bar. Huh? Let's just establish that right away. We're no strangers to this idea of the standard error, but this is partly the reason why we had to develop new terminology. It wasn't obvious in the proportion case, but when we have the standard deviation of x bar that takes the sample standard deviation over root n, that becomes really boggy. So that's why we have a different term, the standard error of x bar. Okay, that's not so scary. Once we know how to find this T star, and I do have the subscript n-1 here, and that's referring to the degrees of freedom. Okay, so the T distribution has degrees of freedom, just the same as the chi-squared did, right? So we've seen that before, where the degrees of freedom dictate the shape. Now, got slides coming up, right? But this means that the sample size will determine the shape of the T distribution. Besides that, everything stays the same. If we do a hypothesis test, it's going to be about mu, right? We're always testing about the parameter. So the null hypothesis is that mu is equal to some mu naught, where of course mu naught is the value that you want to compare your sample mean to. Okay. Just the same as p naught was, mu naught, because we already said what x bar was, it's the sample mean, and so the only new thing here is the mu naught. Mu naught is the value you want to compare x bar to. There's some value that you want to see how X bar relates to that value. How far is X bar from mu naught, taking into account the spread of X bar? Now, what's really, really nice about t-distributions and means in general is notice that the standard error is S over root n, and the standard error is S over root n. Whereas for proportions, we had to remember, okay, is it a confidence interval or a hypothesis test? Because then they use different standard errors. Whereas now we're on just one path and there's only one standard error for means. Okay, and so that's really nice. And we have these degrees of freedom, and I tell you what the degrees of freedom are for each situation, okay, each type of question. So, okay, a little bit early to send you into the pool, but I could give you a question here, and knowing kind of drawing on everything that we've done so far, I I feel like you would be able to put together a confidence interval and you would be able to cobble through a hypothesis test. That's not what I'm expecting, but I think at this point you could. I know you could. So let's talk about the conditions. Let's get those out of the way. Luckily, the conditions for inference for a means question are quite a bit simpler than proportions, and so I tend to rush through them a little bit, but we need to have independent observations, okay? And so as long as observations are independent, which we can get by randomly sampling, right? Random sampling ensures that. And the population distribution is not extremely skewed. What's kind of fun is we can draw from a skewed distribution as long as we have a large enough sample. Okay, then a large sample, just a sample size larger than 30 is usually what we use. Depending on what field you're in, they might say 20 even. But just as a rule of thumb, we'll use a sample size of 30. Okay, so if your sample size is large enough, more than 30, then we have a sampling distribution of the mean, which is nearly normal. Hey, that's great. And we have a standard error of S over root n. Great. So here are just some notes about the normality condition, and maybe I'm not used to having my pen on the side here, but maybe that's better in this case. So the normality condition, uh, the central limit theorem, right, which we've been talking about in all these scenarios, it applies in all these scenarios, then it says that the sampling distribution for X bar is nearly normal. That's great. So if for any sample size, so it holds true for any sample size as long as the population distribution is nearly normal. Now, that's not always the case. Sometimes we are drawing from skewed distributions, and that's okay. Then we just need to make sure that we have a large enough sample, okay? And so here, I'll make a note. We can draw from any distribution as long as n is large enough. Sorry, I kind of squeezed it in there. Oh, now I've done it, haven't I? There. Okay. So, what could you do? You could look at your distribution of your data, and if it follows, so if you make a histogram of your data, it should follow roughly a normal distribution. If it doesn't, then you could say, okay, if I were to sample more, If I were to collect a larger sample, then I would expect it to be normal, and that's your assumption. Okay. Um, this is a little too wordy for me. We'll go to the summary. So we have to have a random sample, okay? Because the observations we said have to be independent, and so the data come from a random sample of size n from the population of interest or a randomized experiment. We're not talking about experiments, and so that's fine. The population has a normal distribution, although usually it's enough that the distribution is symmetric and single peaked unless the sample is very small. If the sample is very small, then it becomes more of a concern. But even then, we would still use the t-distribution. Right? It's pretty rare that we wouldn't. Independence, this is the same as the n less than 10% condition. It's never a problem. And so the population must be much larger than the sample, say at least 20 times as large. Okay, and I'm going to say that this one is optional, just like the other one was. Okay, so when these conditions are satisfied, then the sampling distribution of X bar is nearly normal. Okay? What happens though is we don't know sigma. Sigma is the population standard deviation. And so what we have is we use the sample standard deviation instead as our point estimate for sigma. That gets messy because I have a point estimate for the mean, which is X bar, and I'm introducing a point estimate for the standard deviation, which is S. And I understand that if I were to collect a brand new sample, I would have a new mean and a new standard deviation, sample standard deviation. And so that's where the t-distribution comes from, because it's kind of like, what is it, patting your head and rubbing your stomach at the same time. So these two things can change. That's okay. That's what the t-distribution is for. Okay. And so sometimes what you'll find, or often in reports, but also in some of the questions, okay, it'll report the standard error instead of the standard deviation. Okay, and the standard error is, of course, S over root n. Okay, so sometimes you'll already have S over root n, the standard error. And sometimes you'll be given S and N, and you can find the standard error. Okay. The t-distribution. Okay. The thing about the t-distribution is, okay, so now we don't have the population standard deviation, and that's fine. We're going to estimate it using the, the sample standard deviation. The t-distribution has some similar properties to the z-distribution. It's centered on 0, and it also has a bell shape, okay? But the tails are thicker than the normal models. And so I kind of do this with my arms, okay? And so this is a normal distribution of z, and so then if I have a t-distribution, then what happens is it just kind of pushes down and makes the tails a little bit wider. What does making the tails wider do? Right, the area under the curve is still a probability, and so if the area under the tails is bigger, the probability of seeing more extreme values of t is higher, right? And so the tails are thicker than the normal models. And so observations are more likely to fall beyond 2 standard deviations from the mean than a Z. So we use 2 as a cutoff, but now, especially for small sample sizes, we're going to make that a little bit bigger. Okay. And then just extra thick tails. So here's an image of what I tried to do with my arms. Right, and so the dotted line is the normal distribution, and so the normal distribution falls pretty tight to the axis almost immediately at 3 standard deviations. We know that from the 68, 95, 99.7 rule, and a general t-distribution right, has more area in the tail, more area in the tail, which is a higher probability, right? It's saying, okay, I'm allowing these things to happen. So the probability is larger, right? For these larger values of t. So for the degrees of freedom, I'll highlight this here because it's kind of hard to see. The t-distribution has thicker tails for small sample sizes, and then what happens is the tails get thinner as the sample size increases. Okay, so as you collect more and more of the population, then the t-distribution gets closer and closer to z. Yeah. Now, how we communicate that to the distribution, our sample size, we have the degrees of freedom. And so we calculate the degrees of freedom for a single sample as just n minus 1. Okay? So you have your sample size minus 1, and that's your degrees of freedom. And that's on your formula sheet, right? So you don't need to worry about remembering that or anything. But what happens to the shape of the t-distribution as the degrees of freedom increases? Let's have a look. So it's kind of hard to see, but the faintest line has 1 degree of freedom. The degrees of freedom is n minus 1. Let's make a note of that here. The degrees of freedom is n minus 1, making this a sample size 2. Cute, but not very common, right? So here n is 2, here is n is 3, n is 6, and n is 11. And, right? So I was gonna give it away, but here, what do you think the normal distribution is? N is the population. So once you've collected the entire population size, then you have a normal distribution. It's never going to happen. So if I have a sample of size 2, because that's easier to think about, then I'm expecting my sample mean and my sample standard deviation to be quite unreliable, right? I didn't look at very much of the population. But what we're going to see as the shade of gray gets darker and darker, right? That's as the degrees of freedom are increasing. Even at a sample size of 11, let's have a look. How does it compare to this darkest line? Well, let's see here. Even a sample size 11 is very, very close, right, to the normal distribution. So it's not going to make a huge difference. Once you have a large enough sample size, right, even a sample of size 11 is relatively normally distributed. And so here, a sample of size 2 makes lots of room in the tails, right? And then as we increase our sample size, then the tails close on the axis. Okay. Now, I'm noticing now that I forgot to update these because we have been using the t-table already. And so what I want to do instead of talk here, although this is just a good reminder about what we have been doing, but I want to bring in the t-table. Okay. So we've been using this table, right, to find our p-values. Now, even though we're online, on the test, I'm going to get you to use the tables, okay? And it's possible that you prefer to use Excel, and I'm trying to figure out a way that I could have you choose one or the other, right? But as it stands, you'll have to use the tables to find the p-values, okay? And so just like the assignments. And so I'm sorry. But it's only because I don't want you to have to use Excel in a test situation. So then you can just use the tables. But it is old school, so I don't love that. But okay, so here we are, the t distribution. Okay, we're familiar with using these confidence levels. When do we use these? We use these when I need a critical value for my confidence interval. Let's say I want to make a, let's get crazy, 96% confidence interval. Oh, it's not, it's lagging. Why isn't it showing my pointer? Hello? There. Weird. Okay, it's getting caught up, I think. Yeah. Okay, we're there. So let's make a 96% confidence interval. Usually if I need a Z star, what would I do? I would just bypass all these, hey, wait a second, degrees of freedom. Yes. Okay. And so then I would scroll all the way down to my Z star and I would use 2.054, right? So we already know how to use this table. Now, all these values with degrees of freedom attached to them are t's, right? And so now, if I have, let's say, just as an example, I have 10 degrees of freedom, so a sample size 11, then if I wanted to make a 96% confidence interval, then I would say my t star at 10 degrees of freedom is 2.359. That's not that different from the Z star, right? But it will make a difference in your numbers. Just a little bit wider. Okay? And so now, all right, there's some rules about these degrees of freedom, okay, that I want to talk about. So it's n minus 1, but notice that we only have it increasing by 1 until we hit 30. After that, it increases by 10, 10, 10, 20, 20, and then 900. Big leap. At that point, if we consider the difference between these values here, not a large difference at all. So we don't really need that much precision in our table, but we have it. So I'm expecting you to know how to use it. So what do? You have a sample size of, well, let's go crazy, 800. Then you would have n minus 1. So let's say I have a sample size of 801. I don't want to say 799. Then I have 800 degrees of freedom. So you're choosing between 100 and 1000. Even though it's, for some reason, it's painful, you have to use the 100 because if you went to the 1000, that's assuming that you have a sample size of 1001, which you don't, right? You don't have that much precision. And so, but if you use a 100 degrees of freedom, then you're safe, right? You have more precision than you're claiming to, that's fine. And so in general, you're always going to round down to the nearest degrees of freedom if it's not on the table. Up until 30, it's on the table, so that's fine. Okay. Your sample size doesn't change, right? And so once you have your degrees of freedom, just like in the chi-squared situation, if I have 30 degrees of freedom, I'm stuck on that line. Doesn't help that I kind of had a little squiggle there. There. You're stuck on that line. All the other ones disappear. So you can use it to find your critical value for a 95% confidence interval. What else could you do? Well, by the same methods that we have been using, I can find p-values, right? One-sided or two-sided p-values. I'm going to take my t, the absolute value of t, and I'm going to place it on this line. Let's say it falls here, right? Somewhere between these two values. And then I would follow it down and I have my p-value already. Okay? So nothing really crazy. It's just now we're talking about t's instead of z's, and we're talking about means instead of proportions, but we're already kind of comfortable using this table. So let's see here. Um, so this introduces it as if it's the first time seeing this table, but that's okay. Maybe that's helpful. And so now we've been using the Z table, but we've been using the T table, the Z star of the T table. And so now we're going to use this T table. So let's see here. If you'd been using the Z table, which you could have been this whole time, then using that range for the p-value feels less precise, and it is, but we can still compare that range to the alpha level. So again, there's only positive values for t in the t-table, and that's okay because it's still symmetric around 0, right? So you take the absolute value. So to find the p-value of a t-score, we follow these steps. You're going to calculate the degrees of freedom, which is n minus 1. And then in the left-hand column of the table, you're going to find your degrees of freedom. Okay. And so what I'm going to do here is if the exact degrees of freedom is not listed, you must round down to the nearest line. Oops. So you have to round down your degrees of freedom just to the nearest line. Sometimes I see people have kind of misunderstood and they really round down, but the assignments should help you out with that, right? Because you just round down to the nearest line. So then you're going to move along that row to figure out where the absolute value that you calculated from step 2, so your test statistic, would fall. And so now you've got your fingers on the t-scores just like we had on the Z. I do too many hand gestures. And then what you're going to do is you're going to record them, right? And so you've got some lower t and an upper t surrounding your absolute value of t, just like we did for Z. And then you're going to slide your fingers down to the bottom to find the p-values. And so from the alternative hypothesis, you'll know if you have a one-sided or a two-sided test. I'm going to highlight that because that's really difficult for a lot of people to grasp. So now you have a range for your one-sided or your two-sided p-value, and just make a note that you're going to read this from right to left, right? Because same thing as for Z, as you move into the tail, then your p-values get smaller and smaller. And then you're going to record the range of the p-values that you found, right? Your p-value is somewhere between your lower p and your upper p. And then you can still compare this range of the p-value to the alpha level. I include this because I know at this point, you have an understanding, okay, I should know the p-value. I understand that it seems to be an important part of what we're doing here. But if you're feeling like I don't know what a p-value is, that's totally fine, right? Just take some practice, but also there's nothing I can do but give you the p-value definition, right? And then you just have to absorb this p-value definition. So let me write that down here. Whoops. The p-value is the probability. Oops, can I just say probability of seeing something as extreme or more extreme than what we saw in our sample, than what we saw in our sample, oops, assuming H naught is true. Okay, and so if the probability is small enough, right? So if the p-value is small enough, then you have enough evidence to reject H naught, right? Because assuming that it was true, it's very unlikely that you had seen this, and so that's evidence against H naught. And are we ready for an example? All right. Well, we're going to do one anyways. Now I'm going to, the next slide is the confidence interval. So I'm going to add a page here. Oh, and can I, how do I need lines. There we go. I did it. So our first means example, we're only going to be able to do one example of hypothesis testing and one example of a confidence interval. And so it's going to require a lot of practice on your part, right? Because these are quite long. So unfortunately, that's all we'll have time for, but I'll give you lots of practice. Okay. So I'm starting with hypothesis testing. Usually we've been starting with confidence intervals, but at this point, I suspect that you're more comfortable with confidence intervals, and so I want to tackle the hypothesis testing first. The level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. Yeah, sounds important. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Great. And here are the results in milligrams per liter. Okay, so we've got these 15 measurements at some random spots in the stream. And the mean and the standard deviation of this sample are 4.77 and 0.94, respectively. Okay. That's the information that we're going to have. Now, here, right, one of the easiest way to identify if you have, or easiest ways to identify if you have a means question is if you're given a standard deviation, the only way that's going to happen is if you have numerical data, right? And so if we are given S, the sample standard deviation, it must be a means question. Huh? Now here's the hypothesis test. So a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. That's bad, right? And so is there evidence that the aquatic life is at risk at the alpha equals 0.05 level? Okay, first, let's check the conditions. There's not a lot to the conditions. I'll follow the same format as for the proportions where we did our null and alternative hypothesis first and then check the conditions all in step one. Okay. Step one, oops, is still state the hypotheses. The steps are all the same. What we're doing inside the steps change just slightly, but from our formula sheet, we know that in general, our null hypothesis is that mu is equal to mu naught. Now, the value that I'm interested in comparing my sample mean to right? My sample mean is 4.77. I want to compare that to, I want to compare it to 5, right? 4.77 is less than 5. We are concerned if it is significantly less than 5. Okay? And so here, I'll use a different color. My mu naught is 5. So what I'm going to do here is just replace that mu naught with 5, right? The value I want to compare my sample mean to is 5. We're concerned, and this is going to be our alternative hypothesis, right? We have to assume that 4.77 is not significantly different from 5 unless I have proof otherwise. And in fact, I'm only concerned if it's less than 5. So here, my alternative hypothesis is that mu is less than 5. Just as before, right, in the proportion questions, if I'm only concerned with one of the sides, right, one extreme, then I have a one-sided test. And so I'm going to make a note of that here. And then I'll keep that as a reminder for later when I'm in step 3. Okay. So now we can check the conditions. First, the independence condition. The independence condition, my observations have to be independent of each other, and the way that I can do that is by randomly sampling. And we randomly sampled 15 randomly randomly chosen locations. And so the locations were randomly sampled. So we can assume independence. Now for the normality condition, we said, okay, if the sample size is larger than 30, then we can assume normality, but n is 15, which is less than 30. So we must assume that the distribution is normal. So we must assume, and maybe I'll be proper, the sample was drawn from a normal population. The sample was drawn, I'll say, from a normal distribution, just to use that same terminology. Okay. That's an assumption that we're making. What we could do is here, we could make a histogram of the sample to see if it's approximately normal. To see if it is approximately normal. We don't have that ability here, right? But in Excel we could, and might be worth checking. Those are the conditions, so a lot easier, in my opinion, than proportions. It's just different. So now, therefore, the conditions for the central limit theorem are satisfied. A lot of the time, we're just going to say, yeah, I assume that these conditions are met, and move on. Step 2, do the test, do the do. Or calculate the test statistic. We're getting really good at different test statistics, right? We saw Z, we spent a lot of time with Z, and then we moved to chi-squared. That was a new test statistic. And now we're going to introduce T, which is very similar to Z. Calculate the test statistic. Is really what I mean there. That page. From the formula sheet, let's see, I have it. Okay. Let me. Right. This is our test statistic. T is x bar minus mu naught over S over root n, the standard error of x bar. Okay. We have all these components, and so let's do this calculation here. T is 4.77. X bar was 4.77. I want to know how far is it from 5, right? Mu naught is 5. I'll make a note here. X bar is 4.77. Mu naught was 5. S was 0.97, I think. 0.94, sorry. And N is 15. So S is 0.94 over the square root of 15. I'm going to use Desmos calculator, and let's see here. I want to have both on the screen. Okay, good. You can see that. I want 4.77 minus 5. I'll do it all in one go here. Put brackets around that, divided by, and then the point, I'll do 0.94 divided by the square root of 15, and then I'll close those brackets. Okay. I'll save that, bring it in here. I'm going to crop this up nice and small. I get a T of negative 0.9476. This is very small, right? Just knowing from Zs and Ts are required to be even bigger to reject H naught than 2. And so now what this is saying is that 4.77 is only 0.948 standard errors below 5, not very far at all. And so here, T is roughly negative 0.948, let's say, just to 3 decimal places. The table uses 3 decimal places, and so that's why I round to 3 decimal places. Okay, now I have my test statistic. Next step, right? We're ready to go. We know what we're doing here. It's just a slightly different format. Step 3, find the p-value. First, we need to have our degrees of freedom. So how we're going to formulate this is using the t-table with degrees of freedom equal to n minus 1. Now, I'm going to show the calculation here, especially for the larger calculations later. but I am going to cheat and just put them across the page. So with 14 degrees of freedom, which I know is one of the lines on the t-table, okay, we find, and we're going to set this up the exact same way that we did for the z's. The absolute value of t now, t equal to negative 0.948, is between two values. So the p-value is also going to be between two values. I'm going to specify if I want the one-sided or the two-sided p-value. Notice that I haven't even gone to the t-table yet. I can set this all up and then go to the t-table. I need a one-sided or a two-sided p-value. We were only concerned with one extreme, right? If mu is significantly less than 5. Over 5 seems to be fine for all the fish. So this is a one-sided test. So I'm going to emphasize that here, the one-sided p-value. Just as a reminder to myself that that's the one I want. Okay. So we just determined that we have 14 degrees of freedom. Okay. So what I'm going to do is I'm going to take this block, copy, going to move it in two moves here. Paste image. And I'm going to take this block, copy. There. Okay, these keep going, of course. And so what I'm going to do, right, at 14 degrees of freedom, I'm going to take the absolute value of 0.948, which is 0.948, or sorry, negative 0.948, which is 0.948. And where would it go? We don't get very far. It's somewhere between here and here, 0.868 and 1.076. And so, right, would fall somewhere here. So I write 0.868 and 1.076. Okay. Good. That's the same as the Z star line. It's just now we have degrees of freedom instead, but besides that, nothing crazy is going on. And we said I have a one-sided test, so that means that I'm going to focus just on the one-sided P line, right? These are my P values. And so here, I'm going to go down here and here, and just remembering that this is the one on the right is the smaller value and the one on the left is the bigger value. Because I don't like to think about inequalities, I'm going to just flip them. All right, so 0.15 and 0.20. So my p-value, my one-sided p-value, is somewhere between 0.15 and 0.20. Nice. See? Easy. We learned all the hard things with Z's, and now it just morphs a little bit. How about step 4? Arguably the most important step. Now, what I want to make a note of here is on the test, you're going to have a text box where you put your conclusion. So you have to type it in, okay? And even if you are completely stumped, you don't know what your p-value is, maybe you can't find it, whatever. What I want you to do is just enter a reasonable answer, right? So reasonable answers are any of these, right? And so they have to be kind of next to each other, right? Pretend that you were able to find it. So your answers have to be reasonable. You're not going to get marks for that because it's wrong, but you can use those values in your conclusion. right? So the conclusion is 3 marks, which I'll grade afterwards. So as opposed to test 1 where, it was all just kind of, I adjusted marks because I went through and looked for typos and things, but, there were no open-ended answers, and so I'll mark your answers for your conclusion and interpreting your confidence interval, right? And so there's going to be a lot of marks that you don't get immediately. I give them to you. Okay. And your conclusion hinges on having a p-value, right? So if you tell me what a p-value is, you get it wrong. But as long as you follow through, then I'm able to give you those marks because I'll just look at what you said it was, and then I'll read your conclusion and just make sure that it makes sense, and then I'll give you those marks. Okay, so still the same 3 parts to the conclusion, right? So the conclusion, first we have to compare the p-value to the alpha level. Then, what does that mean in terms of H naught? Do I have enough evidence to reject H naught or not? And then what does it mean in terms of the question? And just because I'm sort of hoping, oops, thought I was in this mode, to keep it on this one page. There. And then I can bump this up. So your conclusion, all right. Our p-value, we said our one-sided p-value is somewhere between 0.15 and 0.20. Oops. Let's say since the one-sided p-value is between 0.15 and 0.20, it is not less than our alpha level. And instead of scrolling all the way up there, I'll just remind you that we were given an alpha level of 0.05. And so it is not less than the alpha level of 0.05, which means we do not have enough evidence to reject H naught. Means we do not have enough evidence to reject H naught. What does that mean in terms of the question? Usually we're trying to reject H naught, and I completely failed. I wanted to have it all on one page, but that's okay. I'll just add a page here. Maybe I'll even bump this down. After all that, I'll still bump it down. Oh well. What does that mean in terms of the question? A dissolved oxygen level below 5 puts aquatic life at risk. Is there evidence that the aquatic life is at risk? No, there isn't, right? It's at risk if we were rejecting H naught in favor of HA, but luckily it means that the aquatic life is not at risk, right? So in this case, that's a good thing. So here, therefore, there is no evidence that the aquatic life is at risk. What we mean here right, is the dissolved oxygen level is not significantly less than 5 milligrams per liter. If you wanted to say that, that's the same thing, right? So that's totally fine. Ha! We did it, right? And maybe I'll say the mean dissolved oxygen level is not significantly less than 5, just to emphasize that it's a means type question. Okay, nice. So what I want to do, let's have some fun, is just talk about the confidence interval. Okay, and so here's an example for the confidence interval. And maybe what I'll do is I'm just going to copy this so it's on this page. And I'll do a little twiddle to show that that's the end of the example, and then I can delete this page. Pair data we're doing next day, so that's fine. So for the confidence interval, I've got a different example. Now we could make a confidence interval for the dissolved oxygen level, but I find that that's kind of boring. So here's a different example. Business bankruptcies in Canada are monitored by the Office of the Superintendent of Bankruptcy Canada, OSB. Included in each report are the assets and liabilities the company declared at the time of the bankruptcy filing. A study is based on a random sample of 75 reports from the current year. The average debt, which is liabilities minus the assets, is 92,000, blah, 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 with a standard deviation of 111,000, blah, blah, blah. First thing you want to do is figure out what type of question this is, right? And so the information that we have, right, it does use the word average. And so that's kind of a telltale sign, right? But also you're given the standard deviation, which you wouldn't be given in a proportion type of question. And so you've already determined that it's a means type of question. And now we've only seen one sample means, but we only have one sample. In fact, it's a sample of size 75. We have the average debt, which is your X bar is, so here I'll put N is 75. X bar is 92,172, and S is 111,538. We're going to construct a 95% confidence interval for the average debt of these companies at the time of filing. Okay, and so here again, if we're making a confidence interval for the average, right, that tells me that this is a means type of question. Okay? And so what I want you to do is for next day, for Thursday, calculate the confidence interval and interpret the interval. And that's where we're going to start. We'll use that for review on Thursday. Okay, so we'll do it together, but I want you to try it on your own because we've picked out all the information that you need. I'll highlight this here. And interpret the interval. You can do it. Got the tools. All right, so we'll end there. If you have any questions, let me know. Otherwise, I'll see you on Thursday.